Delaware Tech, Chemistry 100, Chemistry 110, Unit 6, Gases with Dr. Marc Taylor. In this section, we'll be covering definitions and assumptions about gases. We'll be covering properties of gases, and there are four major properties that are very important whenever you're looking at gases. The number of molecules, N, and we usually count those in moles. The temperature of the gas, and we usually measure that in degrees Kelvin. The volume, and there are various units, including liters and milliliters. And pressure, which has a number of different units: atmospheres, millimeters of mercury, torr, Pascal is the metric unit, etc. We'll talk about the partial pressure gas law. This was devised by John Dalton, the same person who came up with the atomic theory. And then we'll discuss some of the gas laws for Chem 100 and all four of the gas laws for Chem 110. And these four can be combined into a single law called the ideal gas law. The individual laws are volume versus pressure, and this is called Boyle's law. Temperature versus volume, this is Charles's law. Temperature versus pressure, this is Gay-Lussac's law, also known as Amundsen's law. And moles of material, moles of gas, versus the volume of the gas, this is Avogadro's law, the same Avogadro who the Avogadro's constant is named in honor of. In Chem 110, we'll talk about standard temperature and pressure, otherwise known as STP. And in Chem 110 only, we'll be discussing stoichiometry of gases. And this is the calculations that we use to calculate how much gas in terms of volume or mass is derived or used in a chemical equation. So let's talk about some of the basic definitions. Pressure. Pressure is the force of the gas molecules per surface area of the container. Okay, what does that mean? Well, anytime you have a container with gas molecules bouncing around, they're slamming against the walls and slamming against each other, and the force that they exert on the walls for a certain area of the wall is called the pressure. So it is the amount of force divided by the area of the walls themselves. And we can measure this in atmospheres of pressure, torr, or millimeters of mercury, and those two units are exactly the same. This was a unit devised by an Italian scientist named Torricelli, so the millimeter of mercury is also named torr in his honor. The Pascal and the kilopascal are the metric unit of pressure. Volume is just the three-dimensional space or size of any object. So in terms of gas, it's how much space the gas takes up, and we typically measure it in liters, sometimes in milliliters. Oh, and occasionally in meters cubed. Temperature. We know that temperature in everyday life is a measure of hotness and coldness, but to a scientist, it's really a measure of the average kinetic energy of random motions of the particles. So you have the molecules or atoms of a certain gas bouncing around a container, and they may all have a different speed, but on average, the average speed will tell you the average kinetic energy of those molecules or atoms of gas. And from that, we can calculate the temperature, or we could just use a thermometer and measure it. Hot particles move faster and therefore have more kinetic energy, and therefore their temperature is higher. So anytime you're using temperature in a gas law formula, you must use Kelvin degrees. You can't use any other form. You can't use Celsius or centigrade. You can't use Fahrenheit. The number, as I mentioned, is the count of the particles, and we always measure this in moles. Occasionally, another metric unit like millimoles or nanomoles of material, but generally in moles. The partial pressure of a gas is the pressure due to only one gas if you have a mixture of gases. So you may have a lot of gases in your container. For instance, air is composed of many different gases. But if we're only interested in the contribution of the pressure to the pressure due to one gas, That's called the partial pressure. So we can have the partial pressure of oxygen, the partial pressure of nitrogen in the air, the partial pressure of argon, etc. And we'll talk about that when we get to Dalton's law. Now, we also have a concept known as ideal gas versus real gas. The real gas is just what it sounds like. It's the properties of real gases. Gases have these various properties that we talked about, the number, the temperature, the volume, the pressure, and they relate to one another in somewhat complicated ways. But if you make certain assumptions about the gases, in other words, you simplify how you think about the gases, you can treat the gases as this hypothetical version of the gas we call an ideal gas. So this is an ideal gas has two main properties that differ from real gases. We assume that each gas molecule is so small that when we have a container of gas molecules, the gas molecules themselves aren't really occupying much space at all. Most of the volume of the container is the container itself. And then the second assumption we make is that the gas particles don't really interact with one another. They just bounce off of each other and bounce off the walls. So if we make these assumptions, and under many conditions of gases, most conditions, gases behave quote-unquote ideally. However, in more extreme conditions, gases start having these actual interactions between each other, and if you have a lot of gas, they start occupying a significant amount of space, and we can no longer treat them as an ideal gas. For these two classes, all of the gases we're going to assume are behaving ideally. We're not going to look at the more complicated formulas for real gases. STP just means standard temperature and pressure, and this was defined years ago. Now there are two different definitions, but the U.S. still uses the old definition, which is a temperature of 0 degrees centigrade, which translates to 273.15 degrees Kelvin, and a pressure of 1 atmosphere. This is roughly the pressure that we feel just walking around outside and feeling the air pressure on us. The average day would have 1 atmosphere of pressure of gas on us. Diffusion is the net movement of particles, and you can have diffusion in gases, you can have it in liquids, and so you have particles that move typically from one region where there are a lot of those particles, so it's in high concentration, to a region where there are less particles, therefore they're in low concentration. And they eventually spread out just because of random motion, what we call Brownian motion. We won't be discussing this in any detail in these courses, but you should know what diffusion means. It's the movement of particles, this randomized movement of particles, and it tends to go from high concentration to low concentration in order to even out the concentration throughout the container. So ideal gas assumptions, remember we're going to assume that they behave ideally, and the first assumption I already told you is that the particles don't have any volume. In other words, if I crammed all the particles into one corner of the container, they really don't take up that much space compared to the actual container. And we're going to assume that the particles just bounce off of each other, and they're not really attracted to one another, they don't stick to one another. We're going to assume there are no intermolecular forces. This is not true. In fact, neither of these assumptions is true, but they're true enough to make our calculations much, much simpler. So we make these assumptions so that all the math is so much simpler, and the formulas that we use are very straightforward. Real gases behave ideally under most conditions. When they don't behave ideally is when we're at extremely low temperatures or extremely high pressures. Because when we're at very low temperatures, they start sticking to each other. When they're in high pressures, they start sticking to each other, and it typically means there are a lot of particles or they're moving around incredibly fast. And then some of these assumptions and some of the math that we use kind of falls apart, and we have to use more complicated versions of all the formulas, but we will not be doing that in this class. So a couple of watchwords that you're going to see in gas problems about gases. Remember, we talk about the various properties, and these are watchwords to look for in the questions that tell you something about those properties. Sealed means that nothing is going in and nothing is coming out. So we know the number of moles, the N, is constant if you hear the word sealed. Isothermal, as the name might suggest, means the temperature is constant. Iso means the same, thermal means temperature. So the word literally means temperature is the same. So that means if we have a situation where we're changing conditions and somebody says this was done isothermally, it means the original temperature, the temperature initial, is equal to the temperature final. Isobaric means the pressure is constant. So if we have an experiment where we're changing temperature and we're looking at the volume and we say it was done isobarically or in isobaric conditions, iso again means same, baric means heaviness or pressure, so this means the same pressure. Pressure is the same in the beginning as it is in the end. If I say in a steel tank or in a tank, these are solid structures, so the volume can't change, and therefore we know that the initial volume is equal to the final volume, and this becomes important for certain calculations. The technical word for this is isochoric. I won't typically use it, but you should know where the word comes from. And finally, piston or balloon. We know that pistons can get bigger or smaller. We know that balloons can get bigger or smaller. So we know volume can't be constant. We know that we can heat up a piston. We can heat up a balloon, a little bit at least. So therefore, temperature can't be constant unless we say it is. And the pressure can also change. We can pressurize a piston. We can squeeze it to increase the pressure. We can do the same thing with a balloon, or we can decrease the pressure by letting gas out of those objects. So we know that the pressure is not constant. So the only thing we know is constant in a piston or balloon, and that is if it's sealed, is the N. But typically we just know when we hear the word piston or balloon, we know that any of those three things, pressure, volume, or temperature, might vary. And with this, we'll stop here.